Okay, hello everybody and welcome back to another Higher Physics multiple choice walkthrough. This time it's the turn of the 2021 paper, or should I say the 2021 assessment resource. Because there were no exams in 2021, but this paper was issued to schools so that they could use it for internal assessment purposes, and it's now been published on the SQA website, so we can use it for revision for your prelims or your final exams. First thing you see when you open the paper is the data sheet that contains all the numbers that we may well need as we work our way through the paper. And as usual, make sure you have a look at the questions first, try them on your own, and then come back and have a look at this walkthrough to see how you get on or give you a hand with some of the ones you were struggling with. There's 25 questions. The first 10 are usually on our dynamic universe, the next 10 are on particles and waves, and the last 5 questions are usually on electricity. So without more ado, let's dive straight in. Here's question 1. A specially adapted ball has got an electronic timer which starts to time when the ball is released and stops timing when the ball strikes a surface, and the ball's dropped from rest, falls through a height h onto a hard surface, and the time recorded on the ball is 0.4 seconds. And we can ignore air resistance, we have to work out what the height h is. Well, this is a SUVAT question or a TUVAS question or an equations of motion question. So let's write down the 5 variables that we usually see when we do this sort of question. And I'm going to list them as S, U, V, A, T, and we'll fill in what we know. So it's S that we're looking for, that's the vertical displacement. We know it was dropped from rest, so U equals 0. V we're not interested in, that's the final velocity. It's going to accelerate downwards at 9.8 metres per second squared due to gravity. And the time recorded on the ball is 0.4 seconds. So what relationship are we going to use to work out S? We're going to use S equals ut plus a half at squared. Now u is equal to 0, so we can cancel out ut, and we're left with S equals a half times 9.8 times 0.4 squared. And if you do that on your calculator, you'll get an answer of 0.784 is what your calculator display will probably say. So that corresponds to 2 decimal places to answer B, 0.78 metres. That's question 1. Question 2 is graphs of motion. Velocity time graph for an object travelling in a straight line is shown below. Now, it starts off with an initial velocity and then it is slowing down to 0, changes direction and speeds up in the opposite direction. But really all you have to look at here is that the velocity time graph has got a constant negative gradient. So the acceleration time graph will have a constant negative value. And the only one with a constant negative acceleration is answer E. Question 3. The velocity time graph for an object travelling along a straight line is shown. Which row in the table shows the acceleration of the object during the 8 seconds and the displacement of the object at 8 seconds? Well, you can find the acceleration by working out the gradient of the graph, or by using the relationship from your relationship sheet, A equals V minus U over T, where V is the final velocity. In this case it's 10, the initial velocity was 15, and the time taken was 8 seconds. And if you do that on your calculator, it's negative 0.63 metres per second squared. The displacement is the area under the graph. We've got 2 areas there to work out. We've got a rectangle and a triangle. So the area of the rectangle is the base times the height, 8 times 10. And the area of the triangle is a half the base times the height. That's a half of 8 times 5. And if you do that in your calculator, you get a total area of 100, which corresponds to a displacement of 100 metres. So the acceleration minus 0.63, the displacement was 100, that corresponds to answer A. Now you could, of course, also have worked out the displacement using equations of motion. If we used the relationship S equals ut plus a half at squared, substituted in all the values for the initial speed and the time and the acceleration, we would have got the same answer for the displacement. 120 plus minus 20 gives us 100 metres. Same answer. That's pretty tricky. Question 4. A pulling force of 500 newtons is applied to a 60 kilogram block on a slope as shown. The 500 newtons is pulling up the slope, and we have to work out the maximum acceleration of the block. Well, this looks like F equals ma. There's no friction, and so we have to figure out what the unbalanced force is. So first thing we have to do is say, well, what is the component of the weight of the block down the slope? And that's this relationship that we suggest you just remember. The force on the slope, F equals mg sine theta. So 60 times 9.8 times the sine of the angle, which is sine 40, gives you the component of the weight of the block down the slope is equal to 380 newtons. So if there's 380 newtons acting down the slope and 500 newtons acting up the slope, then the unbalanced force acting on the block will be 500 minus 380, which is 120 newtons. That's the unbalanced force that will be making the block accelerate. So we're going to use that in our F equals ma equation. The acceleration is 120 over 60. That's 2 metres per second squared. That's answer A. Question 5. Two objects P and Q of the same mass are dropped from the same height, and the graph shows how the vertical velocities of the two objects vary with time for the first 40 seconds of their fall. And a group of students make the following statements based on information from the graph. Statement 1. The terminal velocity of object P is 50 metres per second. That's the fastest velocity it achieves. That is correct. Statement 2. Object Q reaches its terminal velocity at 10 seconds. Well, no it doesn't. It's just after 10 seconds, maybe 12, 13 seconds. That's incorrect. And statement 3. At 40 seconds, both objects have fallen through the same distance. Well, no they haven't, because remember, the distance gone from a velocity time graph is the area under the graph. And object P has got a larger area under the graph, so object P will have fallen through a greater distance. So if the areas are different, they haven't fallen through the same distance. So it's statement 1 only. That's answer A. Question 6. Total mass of a motorcycle and rider is 250 kilograms, and during braking they're brought to rest from a speed of 16 metres per second in a time of 10 seconds. And we have to work out the maximum energy that could be converted to heat in the brakes. Well, if the motorcycle and rider are moving, they will have kinetic energy. We can work out how much that will be using a half mv squared. Half times 250 times 16 squared. Don't forget to square it. It gives you an answer of 32,000 joules. Now that is the kinetic energy of the motorcycle and the rider, so that is the amount of energy that has to be changed into heat in order to bring the motorcycle to rest. So, energy conservation. Question 6, C. The 10 seconds there, nothing to do with the question. Question 7. A carpenter is building a door frame using a nail gun. The nail gun's got a mass of 5 kilograms and it fires a nail of mass 4 grams. They are both initially at rest, and then afterwards the nail is moving at 150 metres per second, and we have to work out the recoil speed of the nail gun immediately after firing. I think we need a wee diagram here to show us what's happening before and after the nail's been fired. So excuse my terrible diagram here, but on the left there we have the nail in the gun and it's at rest, so initially the momentum is 0. And then it's like an explosion. The nail is moving to the right and the gun recoils to the left. They will both have momentum and the sum of that momentum will be 0. This is conservation of linear momentum here. The total momentum before equals the total momentum after. If it's 0 before, it'll be 0 afterwards. And the only way that that can be is if one of our velocities is negative. So let's call V1 negative. Then we sub all our values in. So the mass of the gun was 5 times negative V1 is equal to the mass of the nail, which was 4 grams. Don't forget to change that into kilograms, 0.004 times the velocity of the nail, 150. And then rearranging that and finding negative V1 will be equal to 0.004 times 150 divided by 5. And that gives us an answer of 0.12 meters per second. And remember, that's in the opposite direction to the velocity of the nail. So that's answer C. Moving on, question 8. The escape velocity of an object is the minimum velocity required to allow the object to escape the gravitational field of a planet. And the following relationship is used to determine the escape velocity. Remember, somewhere in your higher paper there will be an unfamiliar relationship. Don't panic, because all you have to do with this is you will be given enough information so that all you have to do is put the numbers in, rearrange it if necessary, and work out the unknown quantity. In this case, we have to work out V, so it's just a case of subbing in the numbers and working out what V is. So V is the square root of 2g, now you find g on your data sheet, 6.67 times 10 to the minus 11, times m, and you're told m is the mass of the planet, which is 4.87 times 10 to the 24, divided by the radius of the planet, 6.05 times 10 to the 6. And if you do that correctly on your calculator, you will get an answer of 10362.5 blah 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 blah. But we want to round that to 3 sig figs, so it's 1.04 times 10 to the 4 meters per second, and that corresponds to answer D. Question 9. A spacecraft is travelling at 6 times 10 to the 7 meters per second relative to a star. An observer on the spacecraft will measure the speed of light emitted by the star to be... At first glance you might think, I need to do a calculation here, but you don't. If you know Einstein's two postulates upon which his special theory of relativity is based, then you should know that the speed of light is constant for all freely moving observers. So it'll be 3 times 10 to the 8. The speed of light is constant in all inertial frames of reference. Question 10. A spacecraft is travelling at a speed of 0.45 c relative to the Earth. That's 0.45 times the speed of light. And an observer on the Earth measures the time taken for the spacecraft to travel between 2 points to be 72 hours. An observer on the spacecraft measures the time taken to travel between these 2 points to be... I had real trouble with this one. This is really subtle. The observer on the spacecraft will measure a shorter distance between the 2 points than the observer on the Earth will. This is due to length contraction. And bearing that in mind then, the observer on the spacecraft will measure a shorter time to travel between the 2 points. So using that information and our relationship for time dilation, t dashed equals t over the square root of 1 minus v over c all squared, then the t dashed is going to be the observed time on Earth. And it's this t here on the top on the right hand side that we're looking for. That's the proper time as measured on the spacecraft, or in the spacecraft's frame of reference. So rearranging the relationship for t, it'll be t dashed times the square root of 1 minus v over c all squared. And then it's a case of subbing in the number, so 72, and just keep it as 72 hours because your answer will be in hours. 72 times the square root of 1 minus 0.45c over c all squared. The c's will cancel out, and it becomes 72 times the square root of 1 minus 0.45 squared. Make sure that term is bracketed then before you square root it. And if you do that in your calculator, you'll get 64 hours. And 64 hours is the answer we're looking for there. It's answer B, 10B. That is a monster. Question 11. The redshift of light from a distant galaxy is 0.125. That's the redshift ratio, 0.125. And we've to determine the approximate distance to the distant galaxy. So before we do that, we're going to have to work out the recessional velocity using the relationship V equals ZC, or ZZ if you prefer. Z is the redshift ratio, 0.125, times c is the speed of light, and that will give us the recessional velocity, which is 3.75 times 10 to the 7 meters per second. Now you'll notice 3.75 times 10 to the 7 is one of the answers, but that's the recessional velocity, not the distance. If we want the distance, we then have to use the relationship V equals HOD. Rearrange it for D, so D equals V over HO, where HO is the Hubble constant. V is the recessional velocity, 3.75 times 10 to the 7, and the Hubble constant is on your data sheet at the front of the question paper. There it's there, 2.3 times 10 to the minus 18. So let's go back and sub that in, and if you do that on your calculator, then the approximate distance to this distant galaxy is 1.63 times 10 to the 25 meters. That's answer D. Question 12, triple statement question. Student makes the following statements about the universe. Measurements of the velocities of galaxies and their distance from us lead to the theory of the origin of the expanding universe. Well, that's true. The further away that a galaxy is, the faster it's moving away from us. Statement 2, the mass of a galaxy can be estimated by the orbital speed of the stars within it. That's true as well, because from the orbital speed of the stars, we can get an indication of the amount of gravity that's required to keep the stars moving in a circular path, and from that we can get an idea of the mass of the galaxy. So number 2 is true. And number 3, evidence supporting the existence of dark matter comes from the accelerating rate of expansion of the universe. That's incorrect. That would be evidence supporting the existence of dark energy. So 3 is wrong. So 1 and 2 only. That's answer B. And that's all the questions on our dynamic universe. Now we're on to particles and waves. Question 13. Which of the following diagrams represents the electric field between a positive point charge and a negative point charge? Well, the two key facts you need to know here are that the arrows on an electric field diagram show the direction that a positive charge would move if it was placed anywhere in the field. And the second fact is that the arrows should always therefore point away from a positive point charge and towards a negative point charge. So bearing these two things in mind then, let's have a look at these diagrams one at a time. In diagram A then, well, these arrows are pointing away from the negative charge, so they are incorrect. They should be pointing towards it. In diagram B, it all looks pretty good, but let's check the other ones anyway. Diagram C, these arrows are pointing the wrong way, so are these ones. And diagram D, remember in fact all of them are the wrong way around, and in diagram E it's the central arrows that are all pointing the wrong way. So the only one with the arrows pointing in the right direction is answer B. Remember, arrows should always point from a positive to a negative point charge. Answer B. Okay, question 14. the group of matter particles known as fermions. Oh, this is a standard model. I think we should have a look at this little diagram here of the standard model, and if it's fermions we're interested in, that's the green section and the blue section. The green section are the quarks, the blue section are the leptons. So fermions are quarks and leptons only. Pink ones are the bosons, that's the force mediating particles. So fermions, the matter particles. Question 15. A certain type of composite particle is made of two up quarks and a strange quark. The charge on the up quark is plus 2/3 of the charge on an electron, and the charge on a strange quark is minus 1/3 of the charge on an electron. So, if we add all of those charges together, remember there's two up quarks, so 2/3 E plus 2/3 E minus 1/3 E gives us a total charge of plus 1 E. But we also have to decide whether or not the particle is a meson or a baryon. Well, composite particles that are made up of 3 quarks are called baryons, and composite particles made of 2 quarks are called mesons. So in this case, because it was 2 up quarks and a strange quark, it was a baryon with a charge of plus 1 E. That's 15 E. Question 16. 2 changes in a radioactive decay series are shown below. Now I've got 3 different elements here, and this is where your periodic table might come in handy, and there's a periodic table in your relationship sheet booklet. And we can zoom in on the 3 elements in question here. There they are, actinium, thorium and protactinium. And we can instantly see what their atomic numbers are. And in fact, just with that information, you've got a 50-50 choice with the answers. But let's see what's going on here. We've got the thorium emitting a beta particle. Now, a beta particle is a fast-moving electron, and you can represent that in an atomic symbol like this. It's got negligible mass, it's got a charge of -1, and we can use E for the symbol for that. Fast-moving electron. An alpha particle is the same as a helium nucleus, and we can represent it with that atomic symbol. So our thorium, which gives out a beta particle, means the top number is going to stay the same, so it is going to stay at 231, and the bottom number is going to go up by 1. But you would also get that from your periodic table. So this protactinium now gives out an alpha particle. So the top number is going to go down by 4 to 227, and the bottom number goes down by 2, or you'll get actinium's atomic number from your periodic table. So now we know all the numbers: 231, 91, 227, 89. It can only be answer B. Question 17. This is the photoelectric effect. An experiment to demonstrate the photoelectric effect is set up as shown. There's an old-fashioned gold leaf electroscope. The gold leaf will stick out from the metal rod when the metal plate is electrically charged. And we are asked which row in the table shows the charge on the metal plate and the type of incident radiation most likely to cause photoelectric emission. Well, photoelectric emission is when electrons are emitted from the surface of a metal by photons of light, and the plate has to be negatively charged for that to happen. So instantly it can only be A or C or E. But which type of light is most likely to cause this effect? Well, it'll be the one with the highest frequency or the shortest wavelength. And you can use your data sheet here to give you an indication of the sort of wavelengths that are involved. So green light, about 500, ultraviolet, about 400, red, 650, and infrared, about 10,000. So the one with the shortest wavelength there is ultraviolet. So if ultraviolet has got the shortest wavelength, it's got the highest frequency, and therefore it is the one that is going to be most likely to cause photoelectric emission. That's answer E. Question 18. Two identical loudspeakers are connected to a signal generator as shown. This is interference of sound waves. A microphone detects a maximum at position X and it's now moved from X to Y, and as the microphone is moved from X to Y, a series of maxima and minima of sound are detected, and the microphone detects the second minimum at position Y. And we've to figure out the wavelength of the sound. Well, these maximum and minimum regions of sound level are set up due to constructive and destructive interference of the sound waves due to the difference in their path lengths. The path difference to the central maximum is 0 because the paths are the same length. It's half a wavelength to the first minimum, 1 wavelength to the next maximum, and 1.5 wavelengths to the second minimum. So, using that information, and the fact that the geometrical difference between the two paths is 0.6 metres, then 1.5 wavelengths will correspond to 0.6 metres. So 1 wavelength, if you do 0.6 divided by 1.5, is 0.4 metres. So the wavelength of the sound must be 0.4 metres. That corresponds to answer D. Question 19, and this is refraction of light. A ray of red light passes from air into a transparent block as shown. And the first thing to do here is highlight the angle of incidence and the angle of refraction, always measured to the normal. And we have to figure out the speed of light in the block. So straight to your relationship sheet, and there's the relationship for refraction. I've missed out the wavelength part of it because we're only interested in the angles and the speeds. So sine 54 over sine 22 will be equal to the speed of light in air over the speed of light in glass. So let's work out the left hand side first. It comes out at 2.16, and that'll be equal to 3 times 10 to the 8 over V2. I'm now going to rearrange it. So V2 is 3 times 10 to the 8 over 2.16, and you do that in your calculator, you get 1.39 times 10 to the 8 metres per second. That's answer A. Question 20. The diagram shows the path of 3 rays of red light, P, Q and R, in glass. And the rays are incident at the glass-air boundary as shown. So glass at the top, air underneath. And the refractive index of the glass for this light is 1.50. Which of these rays will pass from the glass into the air at this boundary? In other words, which ones will be refracted out? Or more importantly, which ones will be totally internally reflected back in? And to figure that out, we need to know the critical angle of the glass. There's the relationship to find the critical angle. It's 1 over 1.5 and then shift sign. And that will give you an answer on your calculator equal to 42 degrees. That's the critical angle for the glass. Now what that means is that any ray above 42 degrees in the glass is totally internally reflected. So the 60 degree ray in the glass will not be refracted back out again. So it won't pass from glass into air. The 40 degree one and the 20 degree one are below the critical angle, so they will both pass from the glass back out into the air again. So P and Q only, that's 20D. 21. At last, we're on to electricity. 4 resistors connected as shown. It's a mixed series and parallel circuit, and we have to find the total resistance between X and Y. So we'll add the 2 series ones first, the 2 and the 4. That gives us 6 ohms. Then that's 6 ohms in parallel with another 6 ohms. Remember, if the 2 resistors are the same in parallel, the total is half of one of them. So that'll be 3 ohms. And then the 3 ohms added to the 8 ohm gives us a total of 11. National 5 question really there. 21D. Question 22. Another National 5 question really here. We know the resistance and the power of a resistor, and we have to find the voltage across it. So let's list them. Resistance 100, power 4, what's the voltage? Straight to your relationship sheet. We want to find V, so we find V squared first, and then square root it. Square root of 400, 20 volts. 22C. 23, capacitance is measured in farads, so what is 1 farad equivalent to? Well, there's a relationship for capacitance. It's Q over V, coulombs per volt, 1 coulomb per volt. That's 23A. Question 24. A circuit containing a capacitor is set up as shown, and the battery's got negligible internal resistance, and we've to find the maximum charge stored by the capacitor. Well, the capacitor is connected across a 16 ohm resistor, and there are two 16 ohm resistors connected to the 12 volt supply, so they will get an equal share of the supply voltage. That's 6 volts each across those 16 ohm resistors. So we need to use the 6 volts here, not the 12 volts, to calculate the maximum charge. So Q equals CV, that's 20 times 10 to the minus 6, because it's 20 microfarads, times the 6 volts, gives us 1.2 times 10 to the minus 4 coulombs. And that corresponds to answer C. And the final question then, question 25. Again, it's about a capacitor. A circuit is set up as shown. The capacitor is initially uncharged. Switch S is closed and the time for the capacitor to fully charge is recorded. Then the switch is open and the capacitor is discharged. The resistor is replaced by a resistor of greater resistance. That's the only change that's made. There's an awful lot of reading in this question, but really all that's happening is the capacitor is staying the same, it's unchanged. The power supply is unchanged, and we're going to put a bigger resistor in. So the resistor will have a greater resistance. And we're asked which row in the table shows the effect of this change on the time taken to charge the capacitor. Well, it will go up because it'll take longer because there's more resistance. But what about the energy stored? Well, if we use a relationship for energy stored in a capacitor, it's a half CV squared. And if C and V are both unchanged, then the energy will be unchanged. So it stays the same. That's 25D. And that is the end of the multiple choice questions on the 2021 assessment resource. Probably the most difficult one there's been in the past 5 or 6 years, but good revision all the same. Hopefully that's been helpful. We'll see you in the next one.